and 13 deals with a topic that is listed right here. And so let's see how we did with this one. And, well, that's kind of interesting. Because we did, this is one of the first things we did here this semester. A mixture that is homogeneous is said to be a solution. And today what we'll do is we will look at some characteristics of solutions, talk about solubility. Just before we do that, should I remind you that we do need calculators here for the next class. We will be using them pretty much calculating the entire hour. I'd like to remind you of the extra credit opportunities. First of them is due on the 25th at the beginning of class. Next one is due on the May 2nd at the beginning of class. I don't need to give extra credit. So if extra credit is important to you, you'll be sure that it is on time. All right? So if it's late, then that means it wasn't important to you. So if it's important to you, it'll be on time, which means 8 o'clock or before. Yes?
Where are the quizzes for those?
Excuse me?
The quizzes, like you said we had to do the pre and post lab?
There's pre and post lab questions. They're in your packet. There's not quizzes, but fill out whatever you would in there. They're in your packet. There's a set of pre-lab questions, a set of post-lab questions, data. So anything that you write on there to answer the questions before lab, to collect data, and the post-lab questions are all things that you'll be submitting. Okay? Anybody else? Yes?
So you said we were going to get, like, the maximum we can get is 10 points?
Yes.
So if you've been, like, doing the extra credit in Western chemistry, would you be at 10 points right now?
I think I did the math and that it comes darn close. I haven't looked at it, but I mean, there's how many chapters we're doing? I think we're doing 13 chapters, and there's 2 problem sets in each chapter, so 13 times 2 gives you 26. What is 26 times 0.3? Anybody have that? 52, 78, so 7.8. So probably one of them then will get you up to like 9.8. Okay? If you do both of them, that'll put you over the top. So that's just the way, if you want to guarantee for sure to get the maximum amount, it's probably to do both of them. Okay? Anybody else? All right. So we have some terms here with which you need to be familiar. Let's look over these terms. They are solute, solvent, solution, soluble, insoluble, miscible, immiscible, gaseous solution, liquid solution, solid solution, aqueous solution, non-aqueous solution, dilute solution, concentrated solution, unsaturated solution, saturated solution, supersaturated solution, and solubility. So just to have some idea here, and again you're going to be responsible for knowing these, I'm going to quiz you on some of them here, and on each one of these, if you're not sure, please ask a neighbor before you answer. So the first one we're going to look at, if we're dealing with a solution, the stuff that gets dissolved is called what? In a solution, the stuff that gets dissolved is called what? Can you get your answers locked in here, please? We'll count down. 5, 4, 3, 2, 1. Hey, when the chance is 50-50 and we get less than 50-50, that's not very good. So we probably should go through these definitions. If you haven't written them down yet, you should probably start writing them down so you know what they are. Solute. From what we just saw, solute is the stuff that gets dissolved. And the solvent is the stuff into which you dissolve the solute. So if you dissolve sugar in water, put sugar in water. What is the solute?
Sugar.
Sugar. And then the solvent is the water. And when you dissolve sugar in water, you wind up with a material at the end. Now this isn't a sugar solution, but this is an example of a solution here. If you look at this and I ask you how many substances are in here, how many substances does it look like is in here?
One.
Just one. And it looks like one because this mixture is a homogeneous mixture. So that was the first question that came in today. It says another name for homogeneous mixture is, another name for that is a solution. So a solution is a homogeneous mixture in which we dissolve a solute into a solvent. And one of the easy ways to remember this would be to think about water. One of the names of water is the universal solvent. Water is often referred to as the universal solvent. And what does it mean if we say it's the universal solvent?
All around the universe.
It dissolves pretty much anything. Well, that isn't true, but it dissolves a whole bunch of things. Okay? So, next question. Let's look at the next question on here. And again, these are using these terms. So, where are they? Here they are. Come on now, 50-50. If we can't do better than a monkey throwing darts, that's not very good. So let's get up there and see if we get this. If a substance is able to dissolve in a solvent, it is said to be what? So monkey throwing darts is going to at least get 50-50 on this. Unless he misses, of course. All right, so we'll count down. 5, 4, 3, 2, 1. All right, that's better. You must have woke up a little bit. So next one refers to the next terms coming up on here, which is miscible and immiscible. Miscible and immiscible. So which two liquids? Again, I understand we haven't done the definition yet, but just talk with the neighbor if you need to before you guess. You have to answer 2 on this one. Which two liquids are miscible in each other? And you need to select both of them. All right, let's get our answers locked in. We'll count down. 5, 4, 3, 2, 1. Water and alcohol are miscible with each other. What does it mean if we say that they are miscible with each other? They will mix together. So think of the word miscible as mixable. Okay? Miscible and mixable. You can mix alcohol and water together. So that means that immiscible must be ones that don't mix together. So let's see what the next question says. Which two liquids are immiscible in each other? So we'll count down. 5, 4, 3, 2, 1. Water and vegetable oil would be immiscible with each other because, of course, if we put the two together, what happens to the vegetable oil? All right, it separates. Just like we saw when we mixed together the hexane and the water here the other day. Hexane and water would also be a couple substances we could say are immiscible in each other. Or gasoline and water. And, of course, what makes things miscible in each other if we're talking about liquids? What does our general solubility rule say?
Must be an aqueous solution.
No, that's not the general solubility rule. This is from our demo the other day. General solubility rule says likes
Likes.
dissolve likes. Likes dissolve likes. So what that means is that nonpolar dissolves nonpolar, polar dissolves polar. Water, at the end we talked about, is a very polar substance. If it's very polar, it also will dissolve ionic compounds. So again, Likes dissolve likes. So when it comes to these substances, the main reason why vegetable oil does not dissolve into water is because if you know water is polar, that must mean that vegetable oil is nonpolar. Okay, any questions with that one? All right, I guess this refers to the next terms in here, aqueous and non-aqueous. I guess the next ones are here. We skipped these, so I'll come back to these. So the next ones, we'd like to know, a solution in which water is the solvent is called what? Is it an aqueous solution or a non-aqueous solution? So we'll get our answers locked in here and count down. 5, 4, 3, 2, 1. Oh, come on, guys. We need 100%. You guys should know this stuff. This is no-brainer questions, but at least it's better than a monkey. All right? Any questions on this one? Okay, then going back to the ones we skipped here. When you use the terms gaseous solution, liquid solution, solid solution, I think all along you've been programmed into thinking that solutions are always liquids, but they're not. Solutions can come in any phase. They could be solid, liquid, or gaseous. And we use the term solid, liquid, or gas to describe the solution. That means their final phase. And then if you remember what a solution is, we said the solution is a homogeneous mixture. What would be an example of a gaseous mixture? The air. Very simple. The air around us is homogeneous. You look at it, you can't tell that it's made up of nitrogen, oxygen, carbon dioxide, water vapor, whatever else. So air would be an example. Liquid solutions, of course, are the ones we're familiar with. How about a solid solution?
Bronze.
Rocks?
Bronze.
Bronze, yes, bronze would be. We don't have a bronze door over here, but if you look at a metal like bronze, you would see it. Some of our coins, depends upon what it is. A penny is actually, and you've done that one in lab already, haven't you?
Mm-hmm.
A copper-coated penny. But the older pennies, before 1982, those are ones that were a mixture of copper and a small amount of zinc, whatever in there. But you should have found that they were mostly copper. Many of you have them in your mouth. A dental amalgam. A dental amalgam. And amalgam is another name for a filling, a silver filling. And an amalgam is actually, anybody know one element that's in a silver filling? You'd actually be shocked.
Aluminum.
Aluminum is not one. It's actually a fairly toxic element.
Lead.
Not lead, it's mercury. Yeah.
Mercury.
Mercury. So dental amalgams are about 40% mercury. And so that often astounds people because you're actually running around with stuff in your mouth that when we talk about mercury as being something we try to get rid of, and mercury thermometers and everything else, how in the world could we be running around with it in our mouth? Well, it turns out that when we make an amalgam, make an alloy, which is a mixture of mercury and I actually don't even know what all is in there other than mercury because it is toxic, but there's probably some silver in there and some other elements that are combined with it, but it is a homogeneous mixture as a result. And what the mercury does is makes it soft and pliable enough so that you can stuff it in there. But it's not actually the solid mercury that's dangerous to you, it's actually the mercury vapor. So when you inhale mercury vapor, you're actually inhaling individual atoms of mercury, and those individual atoms of mercury then are things that can ionize and wind up going into your bloodstream. But as a solid, they tend to stay locked in there, and those mercury atoms do not escape. All right. Any questions here yet? What are our next terms? Dilute and concentrated. So let's see if we can apply these terms. Now before you answer, talk to someone so you aren't the one that winds up looking like you don't know what you're talking about. Okay, a solution has a relatively large amount of solute is called what? Because I hear a lot of talking. You must know this one. Relatively large amount of solute. Not solvent, but solute. So we'll count down here. 5, 4, 3, 2, 1. This one is a concentrated solution. Remember, a solute is the stuff that we dissolve. So if we have sugar and water, sugar is called the solute. And if we put a whole lot of sugar into some water, that's going to be one that is very concentrated. Exactly. Concentrated means we're packing things together. So one that has a relatively small amount of solute is going to be called a dilute solution. And so they're relative terms. And they often get confused with these next ones we're going to look at, which are the terms unsaturated, saturated, and supersaturated. And now to get these here, we'll go back and start with the term saturated. What does the term saturated mean? Just in general terms, not applied to chemistry, but if something is saturated, what does that mean?
It's filled.
It's filled. So if we have a mop that's saturated, a mop that is saturated is one that is
Heavy with water.
heavy with water. It's very full. Basically, can it hold any more? No. If it's unsaturated, that means it can hold more. And if it's supersaturated, that means that it is probably dripping out of there. So we're going to look at these terms and write down some definitions here. And we'll start with the saturated solution. And a saturated solution is defined like this. We define it as being one that contains the maximum amount of solute that will dissolve in a specified amount of solvent at a given temperature. And as we define this one here, we actually see that there's 3 different variables that are defined or described in this definition. One is the amount of solute, another is the amount of solvent, and what is the third variable?
Temperature.
The temperature. Exactly. So we have 3 variables here that are defined when we look at a saturated solution. And that's because if we change the temperature, we might change the degree of saturation. So we go from here then and we define an unsaturated solution like this. We say that an unsaturated solution is a solution that contains less solute we should say less dissolved solute. That would be better, actually. Less dissolved solute than a saturated solution at the same temperature. So again, it's one that contains less dissolved solute than a saturated solution at the same temperature. Which means that a supersaturated solution, you know what I should do here? I should just copy and paste, but this is one that is going to contain more dissolved solute than a saturated solution at the same temperature. And this one's kind of mind-boggling to some people, because if we say that a saturated solution is one that contains the maximum amount of solute that is dissolved, how can we have more? So I came here today knowing that you were going to ask that question, and so I brought out some demos to show what these things represent. And we're going to start with these two here. And these two here are solutions of sodium chloride. And what I'm going to do is I'm going to put some more sodium chloride into these. I don't have my spatula here, do I? Do you have one? I got one over here. There we go. I'm actually not going to use the spatula for this one though. But we have a couple of solutions now of sodium chloride. And of course sodium chloride is another name for what?
Salt.
Salt, table salt. Okay? And so if we look in here and you compare the two solutions, it should look like the two solutions are the same. In fact, as you look in here, it appears as if there's really just one substance contained in each one of them. So now what I'm going to do is I'm going to place some salt into each one of these, and we'll dump in a fair amount into each one. I don't want to use all of it up, but there we go, that's a fair amount. And we'll stopper these up, and we'll shake them. And we're going to see here now what happens when I do that. I'm trying to think if this is one of them that I have on my app. I don't. Okay, so we'll shake them up here. And I think you should probably notice that this one over here in this hand is clearing up a bit. This one over here still has a whole bunch of solute in it. So now, if I were to ask you which one of these, well, let's not even ask you which one is which. This one here must have been a solution that was originally saturated. Because if it's saturated, that means it's already holding the maximum amount, and it cannot hold or dissolve anymore. This one here must have been unsaturated because it's able to dissolve it. So that means if it was unsaturated, it can dissolve more. Now here's where some people have a little trouble with this. If I were to take this solution now and pour it off and leave the salt crystals behind in here, so if I pour this off and leave the salt crystals behind, the liquid that I retrieve in the next cup, is that going to be saturated, supersaturated, or unsaturated? What is it going to be?
Probably saturated.
It's going to be saturated. In fact, even as it sits here, this solution is a saturated solution. And it's saturated because, remember, when we define supersaturated, a supersaturated one is one that contains more dissolved solute than a saturated solution at the same temperature. So, if it's already holding the max, and I try to dissolve more in and shake the crap out of it like I did, and come back here and look at it, this solution here is still going to be a saturated solution. So then the next question becomes, how in the world can we have a super saturated solution? And so that's what I am going to demonstrate here next. What I'm going to do to help me out with this though is I'm going to put this on my webcam so you can see this. And I didn't want this to run the whole time because it slows everything down. Oh, and it sounds like it wants to make all those sounds, right? So we're going to get feedback if we do this. Is that right? All right. Yep. There we go. We definitely don't want feedback. Okay, so what I'm going to do here now is I have a couple of supersaturated solutions, and the supersaturated solutions that I have are ones that are made of this stuff right here, and they are sodium acetate. And I am going to put this up here so you can see this. That's good. And I'm going to show you how much I plan to dissolve in here, because I want to make sure that everybody has a good idea how much it is. And sometimes it's hard for me when I'm not wearing my glasses to... There we go. Just going to be careful now not to sneeze. Because what I'm going to try to do... to make sure it's still there. Oh, yeah, it is still there. I don't know, can you see the one crystal on the tip? Probably not. Okay, but what I'm going to do here now... No, you can't see it. How can you see it? Fell off. Let's see if I can get this on here. I'm trying to get it so I can... well, I tried on the cam here. So you'll just have to trust me. We'll have Anna, she's been our honest verifier up here. Just don't sneeze. You see that little crystal? Alright, so we're going to take this solution, which is a supersaturated solution of sodium acetate, and we are going... Oh, you need to feel it. We need a couple thermometers. About room temp? Mm-hmm. Okay, there must be somebody else on us besides Anna. About room temp? And a little crystal? Yeah, pretty tiny. It's like one salt crystal. And what we're going to do now, if you look at this, is we're going to take this one crystal and we are going to try to dissolve it into the supersaturated solution. And you can see what's happening now to the solution. All right. So now, as you look at this, and we've had Anna and Valerie verify that this was indeed at room temperature, the next question is on here, when the solute in the supersaturated solution, sodium acetate solution, crystallizes, I predict the temperature did what? Do you predict that it increased, decreased, or stayed the same? What do you think has happened to the temperature? You think it has increased, decreased, or stayed the same? So we'll go ahead and we'll pass this around, and once it gets to the back, then we'll send it over here. And just so we are sure on all this, what I'm going to do now is I'm going to take this one here, which is also a supersaturated solution, and I should have left this on the cam up here. So let me put it back up on the cam, and we will open up our device. We are still on mute, so, and then I need to put this on 16:9. And somebody read that message to me, what it says. It says I can't do something here, but and I suppose this time it didn't pop up, did it? Nope. All right. So we'll try this one out here. So now you can see the flask. We'll move this up just a little closer. And this time, what I'm going to do, remember that this is a solution of sodium acetate. This here is sodium chloride. So I'm going to take this sodium chloride and put it into the sodium acetate solution, and watch what happens when we do. And can you see what happens to those crystals? Those crystals sunk and fell to the bottom. So now what I'm going to do is I'm going to take my sodium acetate and once again try to get one crystal on here and see if I can get that one. There we go. Got a nice size one this time. Just try to see it. I don't think you can you?
I can.
It's just right near the very, very tip. And I don't even want to move over there because if I move over there, I'm probably going to disturb it. But watch now what happens when I put this one in. I drop it in. You see the crystallization beginning to occur. And of course, pop it up here. Go ahead, pass it around and see what happens to the temperature.
No way.
Can you think of a use for that? Can you think of a use for that? There is a use for it. Very common use for it. Hot packs, yeah. We find them in hot packs. I'll take it, they're the same thing now, but one of the common uses of these things is hot packs. In fact, these are solutions now we use from semester to semester, and I have my other colleagues teaching 1020 right now this semester. They're going to use these same things later on today or tomorrow or whatever. How are they going to use these same ones that I just demoed, do you think? Well, not boil them, but very close. I'm going to heat them up, okay? So what I'll do is I'll heat them up, and once I heat them up, that's going to cause the solute in here to redissolve. And once it redissolves, basically I cool it back down to room temperature, and I can use it again. So when we go back and look at the definition that we have for a supersaturated solution, our definition for a supersaturated solution says this: it's one that contains more dissolved solute than a saturated solution at the same temperature. But if I were to, just like this salt solution, try to pour more solute into it, shake the crap out of it, and get it to dissolve, I can't do that. In order to get the stuff to dissolve, I have to basically change the temperature, heat it up, get it to dissolve, and then cool it back down to room temperature. And then at that point, it would be a supersaturated solution. Now, I do have some of those hot packs out here so you can see what I'm talking about. And oh crap. Let's see. Now, of course, as I dropped them, 1, 2, 3, 4 of them, all 4 of them crystallized. So we will take the ones here that I didn't drop and distribute these. Guys in the back never getting close up on this stuff, so we'll put them back here. Who else? Michael, you look like you want something there. And how about somebody up by the front? There, we'll get one. So now, before you do anything with these, I'd like for you to feel the package. Of course, you're going to feel, and this will be the first time that these are actually ever been used. I ordered these last November when I did the same demo in here, because the ones I was just using here crystallized very easily. But in the inside of these packets, when you look at them, you're going to see in the center a small metal disc. And that metal disc is going to be one that you are going to basically press or pinch on it. When you pinch on it, you're going to feel it snap in there. And once it snaps, then you're going to begin to feel the crystallization out. So just so everybody can see it, hold it up so the people around you can see it. Take that metal disc, press on it. And once you press on it, you should hear or feel it click. There you go, just a click, just like that one did there. If you hold it up, you can see what's happening to it. You need to press harder, make it click. You might need to bend it a little bit. You get it? See if somebody else can help you get it. You got it, click?
Yeah, we got it.
All right. You got it? There you go. Okay, now you go ahead, pass those around for the people in your area. teaching so darn many classes right now. I don't remember. Have I passed the salt around yet? Looked in here? Have we passed the salt around, looked at it through a magnifying glass? You see some people nodding, some people don't. I'll just do it again. For those people that have short memories, and I am one of those. Okay? Actually, mine's a long memory. It's a short memory that's the issue. Okay, so what you can do here is if you look at the salt, you can look through here and look at all the shapes of the crystals. You can pass this around to everyone in the back. If you look at the shapes of the salt crystals, what you're going to see is that the salt crystals have the shape of a cube. Okay? And what happens is that down on the submicroscopic level, the ions begin arranging themselves in the cubic pattern, and that cubic pattern then begins to build then in 3 dimensions from there, and eventually gets large enough so that when you see the salt crystals, and we'll try to get it passed around so everybody gets a chance to look at it, please. We will try to, the crystals build up here so they're 3 dimensions, just like they are down here at this level. And what happens then is if we go back and think of what happened when I dropped the crystals in, basically all it took was 1 crystal of sodium acetate to drop in there, and that 1 crystal then caused the entire solution to crystallize. And we call that 1 crystal, we call it a seed crystal. And that seed crystal then basically provides the right instructions for the excess sodium ions and acetate ions to build up on that seed crystal. So now sodium acetate does not have a cubic structure. What sodium acetate has for a crystal structure, I don't know, but it's not a cube like sodium chloride. That's why when I dropped the sodium chloride into here, what happened? It just sunk to the bottom. It didn't crystallize at all. And that's because the shape of this crystal is different than the crystal for sodium acetate. But as soon as I dropped in just even 1 crystal of the sodium acetate, this then was the correct crystal structure that matched the stuff that was dissolved in here. And as a result, the excess amount then wound up crystallizing out of here. Now there is actually, and it's kind of hard to tell in here, there is actually water that's trapped in there. In fact, if you are holding onto these packets right now, these packets aren't solid like this appears solid. These packets remain very pliable in here. That's simply because you're capable of moving it around. And here I can't squish this or whatever like you can squish the ones that you have right there. But if I shake this up hard enough in here, I can loosen that stuff up. And it's basically water that is trapped inside here. In fact, if I was able to squeeze this, I could actually squeeze the water out of there. And if I could squeeze the water out of there, I'd actually be squeezing out and I wouldn't be squeezing out water, I'd be squeezing out a saturated solution of sodium acetate if I could squeeze that out of here. So any questions on this demo? So what are those things used for that I just passed out? Yeah, it's portable heat. They are portable hot packs. And so now that I've used them, if I want to use these again, what am I going to do? Yeah, I'll throw them in water. I'll heat them up. Just put them into some boiling water, and then as I heat it up, it will cause the stuff to dissolve. And then what do I do with it? Cool it back down to room temperature. Once I cool it back down to room temperature, on the inside here we're going to have a supersaturated sodium acetate solution. What is the purpose of the metal disc that's in here? It's to create that seed crystal. So clicking on that metal disc creates that seed crystal, and once that seed crystal is formed, the excess sodium acetate comes out of solution. All right, I need these here so I can demo them for the next class. Thank you.
How many times can you reuse those?
Hundreds of times. Hundreds of times. In fact, I have a really good story here. Anybody else have another one? Okay, thank you. Now these are things that I've been doing, I've been demoing, I've been teaching for almost 30 years now. And in my very first year of teaching, I was teaching down in a small town of Waseca. I don't know if you know where that's at, but it's in southern Minnesota. I was teaching high school down there. And we had a snow day one day. And I said, oh, you know, this would be a great day to redissolve my sodium acetate solutions. Because high school teachers are busy people. And I'm a busy person right now, but nowhere near as busy as I was that first year teaching high school. So this would be a great day to redissolve these. So what I did is I went into my classroom, I took out a hot plate, and I set it onto a hot plate. And I had one of my buddies come by and said, hey Lance, how would you like to go to lunch? I said, yeah, sure, let's go. So we took off for lunch, and we came back about an hour later, and I'm walking down the hallway, and the hallway just reeks of vinegar. Now, why vinegar? Remember, what is this stuff? Sodium acetate. And vinegar is? Anybody know what vinegar is? It is acetic acid. It is acetic acid. So, it's like, oh my gosh, I forgot my sodium acetate on the hot plate, so I go in there. Well, here what had happened is if you look at this, you maybe notice how viscous this solution was before I dropped it in. Imagine this kind of like being a solution of honey. Honey is a supersaturated sugar solution. This here kind of acts like the barrel of a shotgun. Okay? So now, you heat it on the hot plate. If you can imagine trying to boil honey and having this narrow opening here, what do you think is going to happen? It shoots out. Again, just like a barrel of a shotgun. And this happened to be sitting underneath one of these vents right here. So it shot the stuff up into the vents. And then, of course, when it hit the ceiling and came down, I had this stuff that when it hit the table, of course, just like you saw me or heard me drop these things back here, they crystallized instantly when I went in here. These things came down then, and I had the sodium acetate all over my bench, these little drops that had hit all over my bench of the stuff that I had to wipe up and on the floor. And if you can believe it, a chemistry classroom with carpeting is what I was teaching in. So I had to clean all that stuff up. Took a good hour or two. We laughed about it. The next day, I come in and I see these little droplets all over my front bench. It's like, well, what the heck is that? So I get out my sponge, I wipe it up and everything. And then in about 5 minutes, I see these white marks on there where the sodium acetate had crystallized. But here I was confused about it. I didn't know what had happened. So this went on like every day. I'd come in the morning, I'd see these little droplets on my bench. I'd wipe it up and everything, and then about 5 or 10 minutes later, there'd be these white marks in there. Well, what had happened? Well, I kicked it up into the vents. Every morning when the heat kicked on, it dropped these crystals out on my bench. Sodium acetate is hygroscopic, which means it absorbs moisture from the air, which is why I saw the little water droplets. But I wiped it up. When I wiped it, that triggered the crystallization, and then I saw the white crystal marks all wiped up there. In 3 months this went on. Okay? So, this is a great story. So now, year 2 I'm teaching, and I'm down in Waseca, and we have another snow day. And I thought, wow, this would be a great day to redissolve my sodium acetate solutions. So I'm not going to make the same mistake as I did last year, right? So now this year I have 2 because I ruined the one year before. And I said, in case I ruin one, I want another one for my other class, right? So I put them onto the hot plate in my office. My buddy comes by and said, hey Lance, how'd you like to go to lunch? Sure. We take off for lunch. About an hour later, we come walking in the hall. The hallway just reeks of sodium acetate. I go in my office, and my office is coated with sodium acetate all over the walls and ceiling. And so I've told this story for years and years and years. Now I get here, where my classes are bigger and everything, and I used to have all these seats full. We now cut our enrollments down to 48, but we used to have 72 in here. And so we would have all these classes coming through and then tell the story, laugh, ha ha ha. But now instead of having 2 of these things, I would have 4 of these things, right? Okay, so I have a whole bunch of them in here. And so you tell the story and everything. So it's about this time of the semester. Well, you know what happened on Tuesday in here. Tuesday was the last day to withdraw.
Yep.
So I went and ran off after class, and now I have a big hot plate. I put all 4 of them on there. A student came up and started talking to me about withdrawing from the class. And I had these on a hot plate sitting in the prep area. And then pretty soon the lab manager comes around going, Lance, what the heck's in the prep room? So I have 4 of these shotguns going off in the prep room. And so I've now been banned from heating these things. Somebody else takes care of the heating, and they sit and they watch them. But that's kind of what happens. Now, kind of another interesting little tidbit here is that some of you might be familiar with these. Now, don't activate these. I'll pass these around here just a bit. I want these after class is over today. So again, don't open these or activate them. But these here are other hand warmers. And let's see, where else do I have some here? So you can go ahead and look at the package of them. And if you look at the package, you're going to see what the ingredients of these are. On the back side, it talks about the contents. And the contents in here are iron powder, water, salt, activated charcoal, and vermiculite. Okay, so as far as what these things are, these are a little bit different. In fact, once you use these hot packs, what do you do with these? Here, throw them away. These are one-use hot packs, and oh crap, we're frozen up. Okay, there we go. So now the difference on these here is that these carry out a reaction that looks something like this. Basically, that iron powder that's in there will react with oxygen that's in the air. And what do you think they form when you react iron and oxygen? Rust, exactly. And they wind up forming Fe2O3. And so the chemical reaction looks something like this right here. And again, this is because there's 2 different types of hand warmers. And one of the types of hand warmers is the supersaturated sodium acetate that we saw. And then the other type is the iron powder, salt, and water. And that's the one that you have right there. And these are one-use items. And can you see why these here would be one-use items? Because what happens in these? We have a chemical reaction that takes place. So basically what's happening when you open up that package, and don't open it because I want these to demo here, but when you open up this package, that basically exposes them to the oxygen in the air. And once it exposes it to the oxygen in the air, they begin reacting and changing the iron powder that's in there into rust. Now, while these aren't reusable, you can actually prolong the life of these. And how many use these at all? Snowboarding or hunting or skiing, right? Just being outside. Okay. Anybody know how you can prolong the life of these if you only need them for just a little bit?
They can keep shaking up.
Well, not really. What is it they react with? Oxygen. So what do you think we could do to stop this reaction? Don't give it oxygen. You can put it back into a sealed, tightly sealed bag with no air. And so if you can seal it up in a bag with no air, then you can actually not reuse them, but you can extend the life of them, pull them out again, and then they will start reacting. And so now, like I do a lot of skiing, and sometimes my toes get really cold, so I like to put these into my ski boots. One of the problems with ski boots, though, is they have a hard plastic shell, right? And because of the hard plastic shell, if you've sealed up your boots really nice and tight, These aren't very effective because
No oxygen.
no oxygen will get in there. So if you are going to use these, you actually have to make sure that you get a small amount of oxygen that can be used with them. Any idea what the purpose of the salt is in here? It's not a reactant, nor is it a product.
Catalyst.
Catalyst, exactly. Because guess what you have as a catalyst for the iron in your car? Salt, exactly. So that's why here in Minnesota, that salt that's on the road, it's bad in a number of different ways. I mean, it's ruining the environment, but the other thing it's doing is it's basically eating up the iron in your car and turning it into rust. And that's what the water's doing in there as well. It's basically doing the same thing to this packet as it's doing to your car. And actually, if you could feel the rust on your car, you would actually feel that it is giving off heat as it is doing it, as it's going through that chemical reaction. Okay, any questions? Any questions on these? All right, I will want these back. You can pass those into the center here, and I'll collect those. Another term that we need to look at here, we got a few minutes left, is solubility. Oh, you know, it should tell one more here. Solubility. Another one to think about, honey is a supersaturated solution. Honey is supersaturated. If you have honey that sits on your shelf for a long time, what happens to it? Crystallizes. Of course, nobody wants to spread crystallized sugar onto your sandwich or whatever. So if you don't want the crystallized sugar, what do? You heat it back up. Once you heat it up, that sugar will redissolve into the honey, and then you can have it as it's a supersaturated solution. If you ever made rock candy before, okay? If you made rock candy, that's a supersaturated solution. You make a supersaturated sugar solution, and then you basically suspend a sugar crystal on a piece of string, put that into a jar, and then the sugar will begin to crystallize around that sugar crystal, and you can make some rock candy. So, again, some applications of supersaturated solutions. Okay, now solubility. We define solubility like this. We define it as being the maximum amount of solute. It's the maximum amount of solute that may dissolve in a specified amount of solvent at a given temperature. And if you're reading this definition and you say this sounds a whole lot like a saturated solution, you are right. Basically, when we talk about the solubility of a substance, we're talking about what amount of solute is it that will get us to a saturated solution. So again, we look at it, we see that we specify three different variables when we look at solubilities. So when we go from here, we can often take that data then and look at the solubilities. These here are called solubility curves. There's usually solubility, a whole bunch of solubility curves. An individual one in here is called a solubility curve. So again, this is a collection of solubility curves. And solubility curves show the solubilities at various temperatures. Now, if you look at the axes here, you'll see that this axis talks about the grams of solute per 100 grams of water. So it's specifying the amount of solute per amount of solvent. And this axis down below here is the temperature. So we have the three different variables shown on this axis. So now, if we want to talk about the solubility, let's say we talk about the solubility of something like potassium nitrate right here. If we want to know the solubility of potassium nitrate, what we do is, and I've got to see if there's some questions on here, we'd say that the solubility of potassium nitrate is And then we would fill in some data. We would say blank per blank at blank. And so we'd have to specify the 3 different variables. So let's say we want to talk about the solubility of potassium nitrate at a temperature of, and I'll put the scale up above here, this is 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And this is just repeating the temperature scale down below here. So let's say we want to find the solubility of potassium nitrate at 70 degrees Celsius. So if at 70 degrees Celsius we come up to here, we could then put in that temperature of 70 degrees Celsius. And then we'd read the graph from here. And as we read the graph, we see these values. We see that this here is 130, this here is 140. This appears to be about how much? About 139. We could say then that there's 139 grams of KNO3 per every 100 grams of H2O at 100 degrees Celsius. So again, we read the axes here. This is the grams of solute per 100 grams of water at a temperature of 70 degrees Celsius. So let's do another one here. Let's determine the solubility at something like 50 degrees Celsius. At 50 degrees Celsius. So again, and the temperature we're going to pick out here is 50 degrees Celsius. So how do we list that solubility at 50? And 50 sits right here. So we go up right here, and then what do? And then we check it out here, and it looks to be about 85 perhaps. So we could then say that there's 85 grams of KNO3 per 100 grams of water at 50 degrees Celsius. So when we talk about the solubility, we must specify all 3 variables when the solubilities are given. So the solubility is not constant. It's something that changes with temperature. So now, looking at the general trends here, the solid lines here represent solids. The dashed lines here represent gases. So looking at the dashed lines and the solid lines, let's go ahead and answer the next question on the Socratic app. Actually, I have 2 or 3 in a row here. So examine the solubility curves. When the temperature increases, I'll put them back up here. So again, solids are represented by the solid lines, gases represented by the dotted lines. So examine the solubility curves. When the temperature increases, the solubility of solids tends to do what? Look at the data. When the temperature increases, what happens to the solubility? So get your answers locked in here, please. And we'll count down. Count down. 5, 4, 3, 2, 1. And we see that the solubility tends to increase. So you do need to know that fact, that as a general rule, as the temperature increases, the solubility of solids tends to increase as well. Then look at the solubility curves for gases. As we increase the temperature, what tends to happen to the solubility of gases? As we increase the temperature, what happens to the solubility of gases? Does it increase, decrease, or stay the same? So we'll come back here, count down. 5, 4, 3, 2, 1. And we see that they tend to decrease. So again, we see that solids tend to increase their solubility with an increase in temperature. Gases tend to decrease their solubility with an increase in temperature. Now, any ideas how we explain them? Solids are easy. If we increase temperature, what do we do to molecular motion?
Increase motion.
We increase motion. So how do solids get to have more motion? They simply dissolve, right? So by increasing the temperature, we increase molecular motion. If we dissolve them, they are allowed to be more mobile. If we then go to something like gases, once again, as we increase temperature, what happens to molecular motion? Increases as well. How do dissolved gases become more mobile? Well, if they are in solution, they are actually more confined. So the way they become more mobile is simply to escape. So if they escape from a dissolve phase into the air, that allows them to be more mobile, and their solubility then is going to go down. Now there's some applications for this, particularly on the gaseous, well, on each side of them. And one of them we might look at if we were to plot the solubility of oxygen. So again, solubility of oxygen. So we want to look at dissolved oxygen. And on this axis over here, we'd put in solubility. And over here, we'd put in temperature. If we're talking about dissolved oxygen and it follows the trend of all other gases, what would this curve look like? You'd go down, exactly. It would start high and it would go down. Well, of course, if we look at this temperature scale again, going from 0 to 100, if this is a Celsius temperature scale, dissolved oxygen is going to have its greatest solubility at 0 degrees Celsius. So now, again, this starts to have some interesting applications. I know we kind of rushed through this at the end of the hour, but water is very unique on a number of accounts. One of the accounts it's remarkable on is that as a solid, water is less dense than its liquid, which means that solid water will float on liquid water. And that's unusual. For most substances, the solid phase is actually more dense than its liquid. A second unique characteristic is that it has an unusually high boiling point. So we said that water has this unusually high boiling point for its molar mass. If it did not have those strong attractions, we would see water had a boiling point of about maybe minus 80 or minus 90 Celsius. So because of that, scientists look for water in other parts of the universe when they're looking for life. But now, another reason why life is, and the whole density thing, this was kind of where we're running out of here. When ice forms on the surface of lakes. If solid ice or solid water was more dense than water, what would happen is that the ice would form on the surface and
It would
sink to the bottom. Form on the surface and sink to the bottom. And keep doing that until eventually what would happen is the lakes are going to freeze over solid. And so because of that then, life can be sustained underneath the ice here in Minnesota. But another thing that helps keep life sustained is the solubility of oxygen. So turns out that oxygen has its greatest solubility at 0 degrees Celsius, which is at the same temperature at which water freezes. So in the winter, once the lakes freeze over here in Minnesota, they freezed over, and at that time they're holding the maximum amount of oxygen that they can possibly hold at that temperature. And so the life under the ice can survive throughout the winter, like the aquatic life, like fish and whatever else, because of the fact that they have a whole large supply of oxygen. Now sometimes what happens in Minnesota winters is, if we have a very hard winter, of course we basically cut off the supply to oxygen from the atmosphere. And so there are times, and especially in shallow lakes in Minnesota, they open up what's called promiscuous fishing, which basically means they allow fishing with no limits. And part of the reason why they do that is because they want to remove as many fish out of the water as possible, because what are fish going to do? They're going to die, and they're also consuming the oxygen. So very often then, when we have very, very difficult winters here in Minnesota, to prevent an entire fish kill, they'll open up what's called promiscuous fishing, which basically enables you to take as many fish as you want out of a shallow body of water to prevent all of the fish in that lake from dying. So that's just a couple of examples. Now, one of the things that I used to do when I was a student just like you, I worked at an electric power plant, and we were trying to find the effect of the electric power plant on the ecology of the Missouri River. I was living down in Sioux City at the time, down in Iowa, and one of the concerns is what we call thermal pollution. Now this is perhaps a type of pollution you've not heard of before. Usually when you think of pollution, you think of pollution as being chemicals and such. But thermal pollution has nothing to do with chemicals. Thermal pollution has to do with heat. Okay? So what happens now, if you're in an electric power plant, you often need to have access to a big body of water. I don't know if any of you have ever been up by Monticello before, our big lake. You see the big power plants that are up there, right on the Missouri River. You go through in the winter and you're going to see that they have big clouds of steam that are coming out of the stacks there. Well, what happens is that they have huge, huge, huge generators that they have to take water in from the river and discharge it further back on down. If you've ever been through Monticello in the winter, what's one thing Monticello is known for in the winter?
Open rivers.
What's that?
Open rivers.
Open rivers. And what's in those open rivers? Fish, but there's also a whole bunch of trumpeter swans. If you've never been in Monticello, they're known for trumpeter swans in the winter. And if you go down to Red Wing, if you've ever been down to Red Wing, in the middle of winter, what do you find down there? Bald eagles. Okay, so, and that's because there's a big power plant that sits down the river down there. So down in Red Wing, you got the bald eagles that fish. Up in Monticello, you have the trumpeter swans. But the river stays open, and the river stays open because of the warm water. And of course, when you have warm water, what is that doing to the solubility of the oxygen in the water? Causing it to decrease. And so now, in the summer, that's an even bigger issue, because when the weather gets warm here, if that temperature gets too high, eventually it's going to get down to the point where the amount of dissolved oxygen in the water is going to be too small or too low to support fish, and then fish begin to die as a result. So when I was working at the power plant, one of the designs of the power plant was this. The power plant sat up on a hill, and coming out of the hill, which sat up here, so we'll put the power plant up here. It's got this big old smokestack sitting up there. And then coming out of here, down below, is the river. Okay, well, coming out of the power plant then was something that looked kind of like this. And what happened then is that they discharge water back into the river over one of these mechanisms. And what do you suppose the purpose of this mechanism here is to do? Cool it and add in oxygen. So by causing it to turn over, just like waterfalls, that exposes more of that water to the air as droplets. You may remember when you did the lab that when water evaporates, it will cool. And so by basically making them smaller droplets, it's more likely for them to evaporate. Those water droplets will cool off, and they will also take in oxygen from the air as you expose smaller and smaller droplets to the air. So that's one of the ways they combat thermal pollution, is to have one of these mechanisms in place. When you put in a new housing development, you may notice how this didn't happen when I was a kid, but today when they put a new housing development in, they put up these big fences or silt barriers around there for a couple reasons. One of the reasons is you don't want like dirt and stuff flowing into the creeks and rivers and whatever else. But another big reason happens to do with thermal pollution. Because what happens in the summer? When do we usually have storms in the summer? When the weather is been really hot and humid, right? So when it's been really hot and humid, it's often come on a sunny day, the sun is going to beat down onto the pavement, and the pavement's going to get really hot. So the rain comes down, lands on that pavement. Once it lands on that pavement, that water gets really warm. Well, where does that water go once it lands on the road? It doesn't evaporate. Some of it will. But it goes into storm sewers, and where do those storm sewers go? Back in the rivers. So what does that do to the temperature of the water in the river? Causes it to go up. What does that do to the solubility of the oxygen? Causes it to go down. So when developments go in these days, especially if you're around things like trout streams and such, trout are fish that need really, really cold temperatures. So basically, you are looking very carefully these days at where that water is being discharged, because if you discharge warm water into something like a trout stream, you're just going to kill off a whole bunch of fish when that happens. So that's why today, why we do have some of these protections in place from very simple things such as thermal pollution. We're not even talking about a chemical here. So, any questions that you have on this stuff? Okay, last thing. We got about 3 minutes left. I have one question left here. We're going to start on Thursday talking about concentration. And we're going to look at concentration units. When we talk about how concentrated something is, we're trying to tell how much solute there is per amount of solvent. Which of these units here could be used to represent concentration? And talk with a neighbor here. There are 3 or more answers here. 3 or more. All right, let's get your answers locked in here, please. We're not done yet, so we'll count down. 5, 4, 3, 2, 1. And basically, if you see anything where it's something per one unit per another, that's going to be something that is concentration. So coulombs, that doesn't measure concentration, that's a weight. Kilometers is a distance. Milliliters is a volume. Kilograms is a weight or mass. Cubic centimeters is a
area.
Volume. So the rest of these here are ones that we'll look at then on Tuesday. That's it.